Hello, in today's podcast I'd like to talk about the basics of circuits. Specifically, I want to define current and potential. Both of these terms are things you should have heard before in introductory physics. I want to make sure we understand what those things mean and then go on and use them in some specific ways. The two most important quantities in electronics are current and potential. Both these quantities, they're easy to measure, which makes them important because it's good to have things that are easy to measure. And two, they describe a situation. There are enough variables that we can describe what's going on in some situation, sort of like energy and speed in mechanics. So let's start with the current. Current is a little more straightforward. The current is the amount of charge that passes some point in a given interval of time. So represented in this picture, we have charges moving through a wire. We could pick some cross-sectional area and count how much charge goes past some point in some unit time. It's defined in the following way, where N is the particle density, how many particles are there per unit volume. E is the electric, how much charge does an electron have. A is the cross-sectional area of the wire, and V is the speed of the charges as they move through the wire. And so you can see that NE is sort of how much charge is there per unit volume in the wire, and the A times the velocity defines some volume that passes some point per unit time. And so that's the current, relatively straightforward amount of charge that passes some point in a given time. Now let's go back and set up the potential, right? And to do that, we'll go back and talk about electric force and talk about Coulomb's law. And basically we said, hey, in experiments, if we have two charges, they interact, and we can describe that interaction using Coulomb's law, which is described by the following equation. What's that mean? If we take some charge Q1, it has some amount of charge, and we bring some other charge, we'll call it Q test, usually some smaller amount of charge, we can determine the force, and the force is proportional to the amount of charge that we have, the amount of test charge that there is, and inversely proportional to the distance between them, and specifically the distance squared. And so we see that the force is in line with the two charges and given by the following equation. And so that's fine. We can calculate the force, we can use all the mechanics, and we can explain what happens with charges. In the end, that wasn't that convenient, and so we just defined the electric field, right? It's the same thing, but we just describe it in a different way. And so in this way, we say we place that charge Q1 out there, and that charge distorts space in some way. It creates some kind of a field, and that field is dependent totally on charge Q1. Now if we come and bring the test charge into that field, then it'll interact with the field and it'll experience some force. Now this will be the same force that's described by Coulomb's law. In the end, we're just describing some other way of doing it. Now the benefit of doing this way is that we don't have to worry about the test charge. What charge is it? 1 coulomb, 2 coulombs, 3 coulombs. The field only depends on this charge Q1. And we define the electric field as the force on the test charge divided by the amount of test charge that we put there. So practically speaking, if you wanted to figure out the electric field, you'd put some charge Q1 in there, go to some distance r, you'd place the test charge, you'd figure out the force, divide that force by the amount of charge, and that gives you the electric field, which is essentially the force per unit charge at some particular point. Okay, so we have two ways of describing, sort of from a force perspective, the interaction between two charges. We can also describe it using potential energy, right? And so we can take the standard definition of potential energy from Physics 141, and we can write down what's the force between the two particles. Well, that's just the charge times the electric field. And so we could figure out what's the potential energy of moving the test charge, say from infinity to some point a distance r away from our Q1. Well, that's not that practical either. That depends on the test charge, and so what we further did is we defined the electric potential. The electric potential is defined in the following way. It's essentially the potential energy per unit charge. And it's represented by this V. and where V at R naught defines the zero of potential energy. So just like gravitational potential energy in mechanics, you could arbitrarily define zero to be at the floor or at the ceiling or wherever you wanted. The same holds true in electricity and magnetism. So the